All right, guys, so in this video, the real goal of this video in particular is actually sort of diving into some real definitions of how velocity, acceleration, and speed are represented as vectors. Before we sit there and simply say, hey, here are the definitions, I want to kind of think for a second as an example of how it actually is utilized in application itself. Because we've already talked about position, velocity, and acceleration. And if you remember correctly, we said that position, all right, is your starting point, right? And then velocity is your derivative of position, and thus acceleration is your derivative of velocity, or the second derivative of position. And so we're going to look into this again and kind of refresh our memory a little bit of derivatives. And so the example we see here says that a particle moves in the plane so that its position at any time greater than or equal to 0 is given by our sine t and comma t squared over 2. So that's going to be its position at any time that t is greater than or equal to 0. All right. So first and foremost, we got to find part A, which says the position vector of the particle at time t. Well, let's say that you started at nothing, right? And it said that at any point in time, you can find it represented by a point sine t comma t squared over 2. So your x component is sine t, your y component is t squared over 2. Well, how do we really kind of represent this in terms of a position? Well, if I started at 0 and I needed to move in some way that gave me sine of t, well, I'm going to end up looking at the component of moving in the x direction, sine of t, and moving in the y direction, t squared over 2. That's it. That's all it is. And so what about part B? Part B says, find the velocity vector of the particle at time t. Well, if velocity is equal to, and we'll go ahead and call r of t position. I think we used s of t in the past, but you're going to see in the book it uses r of t a lot, so I want to keep it consistent. So the velocity is r prime of t, so this is equal to r of t. So r prime of t. Well, what's the velocity that we were looking at? Well, the velocity of our above function. So in this case, velocity. Well, what's the derivative of sine? Well, the derivative of sine is going to be cosine. And then what is the derivative of t squared over 2? Well, think about the power rule. Bring the power down, and so you have 2t over 2, and 2t divided by 2 is just t. And so now our velocity, the derivative of position, is cosine tt. That's our component form for the vector velocity. All right. Well, now what about acceleration? Well, acceleration, we now want velocity, right? And I probably should be writing these in terms of vectors, all right? But it's kind of imagine that these are all vectors, not really functions. They're vectors, all right? Our acceleration, not velocity, is equal to the derivative of velocity here. And so the derivative of cosine is negative sine of t, and the derivative of t is just, well, it's just 1. And lastly, it says, describe the position and motion of the particle at time of t equaling 6. So now all of a sudden we have to start thinking to ourselves, well, all right, where are we going to find or a description of the position and the motion? Where is it going at all of these particular places? All right, well, let's take a look. The particle is at the point, so let's go ahead and look at part D. I'm going to change colors here too. All right, so for part D, we want to find out where is the particle at time equals 6. Well, where is it going to be found? Well, that's position. So that's really thinking r of 6. And so we're going to be at sine of 6. And t squared, so 36 divided by 2, 18. Okay, so there's the component form of our particular particle. And since this is a particle, it's really a position. This, you can go ahead and just make this the actual point itself. Whoops. Of parentheses and not our little arrow brackets. Okay, well now what happens with the velocity? Is the velocity positive? Is it negative? Is it going forward, backward? Where is it going when time equals 6? Well, v of 6 in this case is cosine of 6 comma 6. So everything's positive in this case. Everything's positive in this case. And then it says, finally, for acceleration, we went ahead and said, hey, a of 6. And so we have negative sine of 6 still at 1. Okay, so still at 1. And so kind of thinking about what this all, I guess, is actually representing here. If we did go ahead and graph this, you can kind of graph it in mode of parametrics. And I guess let's go ahead and graph this real quick, actually. Let's go ahead and graph this. So let's take a look here. Let's go ahead and graph this. I apologize for not having this up already, but kind of pulling a little mulligan, pulling a little audible. All right, so let's go ahead and graph this and kind of see what the opportunity is to graph. And so we want to go ahead and to put it first and foremost into parametric mode. So we're going to go ahead and graph this in parametric mode. Then when you go to the y equals, you start noticing a little bit different in this case. And so we're going to go ahead and graph the position when x equals sine of t. So x equals sine of t. And then your other position was y equals t squared. So t squared over 2. Let's take a look at this graph. You can kind of see our graph kind of floating through in here. Let me maybe change this window a little bit because we need to get a little bit higher on the y side of things. So let's go ahead and change this window. I guess we'll go to 8. It'll probably give us a good visual there. All right. So, well, let me go a little bit higher actually. Still quite not high enough. I guess we'll just kind of go up all the way to 20 here. Let's see what happens. All right, we started to kind of come back a little bit. We're starting to get a little bit more of the gist. All right, but anyway, the purpose of kind of showing how this graph looks is, one, how to graph your parametrics and kind of seeing how actually this particle is moving itself. Okay, but when t equals 6, you can kind of get somewhat of a visual from 0 to 6, I guess, specifically. All right, the point sine of 6, 18, represents the velocity vector of cosine 6 comma 6. It shows both the magnitude and the direction. So once we have gone ahead and said, hey, at sine of 6 comma 18, there is our point. All right, so somewhere roughly, I don't know, in this direction up here, because I did 20 at the top, so probably right around here or so. So here's sine of 6 comma 18. And then the velocity vector would go kind of in that straight motion right through here. So we would have the velocity vector being created going to the right cosine of 6 and going up a value of 6. And so you kind of can see exactly how it's being moved around as well. And so not always necessary to see the graph of it. I kind of thought it would be cool to kind of throw it in there as well too. And that's going to lead us into our definitions. That our 5 different parts of thinking of velocity, speed, acceleration, and the direction of the motion. So of course we start off of our position vector. We normally see it as r of t or s of t. Then of course the derivative of position is velocity. So derivative of both the x and the y functions inside of the vector. The speed, extremely important. Our speed is the magnitude of velocity. So it is your distance formula, basically, of our actual velocity components. And always keep in mind, guys, that speed is a scalar. It is not a vector. We talked about that in the very first video. Lastly, acceleration is going to end up being our second derivative of position or our first derivative of velocity. And then we've already talked about the direction vector as well too, guys. But this is our direction of motion, the vector over the magnitude. All right, so our direction of motion is going to be our vector over our magnitude of the vector as well. All right, so let's take a look here real quick as we continue to look through some of these. So our next example in here, we're going to look at some more planar motion. So let's say, for instance, that we see that a particle moves in a plane with position of vector r of t, sine 3t and cosine 5t. Find the velocity and the acceleration and determine the path of the particle. Well, let's go ahead and find out what the velocity is. If r of t, we've already said that r of t is equal to sine 3t, and the y coordinate is cosine of 5t, cosine of 5t in there. And like I said, I really should be either bolding these r's or putting the little thing under it as well too, to identify that they are not just function, but they are vectors themselves. So velocity in this case will be the derivative of sine. So chain rule. So the inside is 3t, so the derivative of 3, our 3t is just 3, and the derivative of sine is cosine, so cosine of 3t. And then we've got for cosine, well, cosine is negative sine times the derivative of the inside, so negative 5 sine of 5t. Now we want acceleration as well too. Again, acceleration is the derivative of our velocity. So the derivative of cosine of 3t is going to be negative 3, but multiplied by the 3 on the outside. So we have negative 9 sine of 3t. And then again, we have sine being cosine, but the derivative of the inside function is 5. So 5 times the negative 5 becomes negative 25 of cosine 5t. All right, so what about the path of the particle, though? All right, what about the path of the particle? So we've gone ahead and we found velocity, we found acceleration, and now we got to kind of find out what this path for the particle is going to be in the end. Well, I wish I could just say, hey, the path is, north or south. It's not always the case. And sometimes vectors are extremely simple like that, but usually not so much. And so we talk about particles especially. I mean, sine 3t, cosine 5t, that's a position of the particle. So how is it actually moving? So I went ahead and graphed this one for us. And so this is what we're looking at. So to describe the path of it, well, you're looking at the path of it. It's all kind of over the place and it's pretty jumbled. And if you kind of think about a particle moving in motion, you don't usually always think of a particle just necessarily like an atom or whatever the case is, always just going in a straight direction. And so the path of the particle, obviously is kind of strange. But what you do kind of want to look at certain points is, where necessarily would be the particle at a given moment in time? Like what direction is it moving in, right? Is it moving in a positive direction on the x-axis, but maybe a negative direction, at a certain point in time? And so, again, like you might be asked for a particular spot. I don't know, we're just going to makeshift and call this, 1/2 or pi over 4. Is probably what it actually is here. I can't exactly see. But let's say, for instance, we're looking in this direction here. Obviously, it is kind of going in that upward direction towards positive x's and positive y's. But it's about to start making its velocity. It means it's going to start making its way back down. All right, you can obviously see that the position is going back on down. That means it starts to slow down at this point, right? And so when velocity starts slowing down, we're starting to decrease those values a little bit more so. And so to graph, guys, remember, guys, when we're graphing our parametrics, you're going to make sure that your mode is in parametric form, all right, parametric form. And then when your y equals, you'll have sine. You'll see that when you click your xt theta n button, you're going to end up seeing that t will pop on up. And so this is what you'll end up getting. And it's kind of more so just kind of fun to see exactly what it all looks like when it's in that plane of motion as well too. Okay. All right, guys, that is going to wrap it up for this one, and we're on to the next one.